Okay, honors kids, here's our next two pages of the review packet. Start from the top. It says, determine if a valid conclusion can be reached from the two true statements. If it can, state it and the law that is used. If there is no valid conclusion, write no conclusion. We're also going to touch on why there's no conclusion if that's the case. So you might recognize this problem. It says, if a mineral is gypsum, then the word then is not there, but it says it has a hardness of 2. A lot of times there's an implied then. The statement's still a conditional statement because something has to happen before the second part can happen. But the word if needs to be there, but sometimes there'll be an implied then. Then we have if a mineral has a hardness of 2, well, that's just Q again. So remember we had P, Q, here's Q again. Then it can be scratched with a fingernail. Well, that's totally new, so we're going to call that R. Well, we have two conditional statements, so this would be a law of syllogism problem if it works. So let's see if we can make our train. We can make our train, so our conclusion would be if P, then R. So our conclusion is if a mineral is gypsum, then it can be scratched with a fingernail. This is just a common shorthand for with W slash, and then W slash O would be without. The law that we used was the law of syllogism. So let's move on. It rains after school, so if it rains after school, then field hockey practice will be canceled. There is Q. Practice is canceled. Well, practice is canceled lines up with Q. To use the law of detachment, we say we have to have a conditional statement, and the first thing has to happen, but it didn't. We don't know that it rained after school, so we can't conclude that practice was canceled. When we know practice was canceled, we don't know why. It could be because of construction, it could be because of snow, it could be for various reasons. Maybe the coach had to stay home sick. So we can't make a conclusion using the law of detachment, and we don't have anything that lets us make a conclusion at this point, so no conclusion, no law was used. Okay, provide a real-life example of these two things. We want you guys to try these on your own. Just remember, for the law of detachment, you're giving one conditional statement. The first thing happens, so your conclusion is the second part happens. For the law of syllogism, you need two different conditional statements, and then the end of one needs to match up with the beginning of the next. Your conclusion is a new conditional statement. So you guys are going to need to try those on your own. But let's do these Venn diagrams together. So we need to either write a conditional statement or use the words all, sometimes, or never to write a statement. You could use always instead of all, or some instead of sometimes, but we need to use those types of words. So for number 22, we actually have a lot of options for what we can do. I'll do all of them for this one. The first option would be to do an if-then statement, since we have a circle completely inside the other. We call these concentric circles. So we could say if you are a wheat, or if you are wheat, then you are a grain. That's one option. We could also say that all wheat is grain. We could also say that some grains are wheat. So notice for this first one, we had a lot of different options. We could have done it as an if-then. We could have used the word all or the word some. You could also do sometimes. So you could say sometimes grains are wheat. For 23, we also have a lot of options. We could say if you are a pitcher, then you are a baseball player. If you are a pitcher, then you are an athlete. We could say if you are a baseball player, then you are an athlete. We could say some athletes are baseball players, some athletes are pitchers. We could say all pitchers are baseball players, all pitchers are athletes, or all baseball players are athletes. I'm just going to do one of them. Or actually, I'm not going to put any of those down. If you just listened, that you could have gotten that. But there's going to be multiple answers for this. Multiple answers. So an example here, I will put one, would be that all pitchers are athletes. That's just one example of what you could put. Our keyword there was all, but you could also do a some or if then. Number 24, we have this Venn diagram. It's one that you're probably used to seeing before this, and you'll notice these two sections overlap there in the middle. So the only word we can use is some, because some of this circle intercepts with some of this circle, or intersects, I'm sorry. So we're going to say sometimes something that tastes good is good for you. So our only option here was sometimes. That's our only option. And I'm going to put up here that you had 3 options. 25. Notice that these two ovals don't intersect at all, so we have to use the word never or none. So we could say, either we could say that no turtles are snakes. You could have put turtles are never snakes. Same thing. I'll put that in parentheses. You could shoot turtles, whoopsies, are never snakes. It's the same thing. We won't be that picky as long as that meaning is there. So let's flip to the back page. Getting close. Here's topic 6. So first we want the meanings of a couple of terms. So for postulate, a postulate is something that is accepted without proof, or I'm going to say accepted as true without proof. A theorem is similar, but a theorem has to be proven to be accepted as true. So I'm going to put must be proven, oopsies, I can't spell today, proven to be accepted as true. And then a definition is the meaning of a given term. I'm just going to elaborate on them really fast. So a postulate versus a theorem, we always need to start somewhere. And also, guys, pardon my thing on my hand. I have my own online class I have to finish. That's my reminder. So postulates versus theorems. A postulate is like a starting block. So if we're going to build something, we have to have somewhere to start, right? So if theorems have to be proven to be true, we need something to help prove that first theorem, and that's what a postulate is. So the linear pair postulate is an example. We use it to prove the vertical angles theorem. We use it to prove other things, and we need that starting point. A theorem we know has been proven in order to be considered as true. They're very, very similar, though. Definition is what gives, like, so in a proof, if you're using a definition, it might be for something like this. Let's say that your first step is that angle 1 is congruent to angle 2. But you need to then say that the measure of angle 1 equals the measure of angle 2. We can use the definition of congruence to get from here to here, because the definition is that if two angles are congruent, their measures are the same, or they're the same size angle. So that's why we would use a definition in a proof. So let's keep moving on. Here's 3 properties that we want to make sure you know. There's more of them on our list. In our notes, we did it in the notes for topics 6B through C, as well as that purple reasons for proof paper that you have. And I remember, if you're in my class, I gave you guys a hint that whenever you see 1 equal sign, it's reflexive. When you see 2 equal sign, it's symmetric. When you see 3 equal signs, it's transitive. And conveniently, that also puts these into alphabetical order. So when something is equal to itself, it's the reflexive property. In this case, it's a property of equality because we have an equal sign. For step 2, we have something is equal to something new, but then we switch the sides that they were on. That's our symmetric property of equality. Oopsies, up here I put a C. I meant to put equality. And then for number 29, we have something, and let me mark this up. We have something is equal to something new. That same something is congruent to something else, and so since those 2 things, B, C, and F, G, were equal to the same thing, we know that these also have to be the same size. That's their conclusion there. That's our transitive property of equality, because we have the equal sign. So once again, 1 equal sign, 2 equal sign, 3 equal sign, alphabetical order, which is convenient. Okay, let's finish up with just 2 proofs really fast. This is an algebraic proof, so we like to start by first solving. So this is what we are starting with. That's our given information. Well, next we're going to distribute that -3. So that's going to give us -6 plus 3x. Notice that negative with that negative makes it positive. And then we distribute on this side and get 5x plus 20. So that was the distributive property. We don't call it a distributive property of equality, mainly just because when you're distributing, you're only distributing on one side of the equal sign, so it doesn't really matter if there's an equal sign in the middle or not. We can do that regardless. So if that makes sense, great. If it doesn't, don't stress about it, but just the distributive property. Next, I'm going to subtract 3x on both sides. Oh, wow, I did not do that. Woo! Mrs. Barnes. There we go, 2x. Because remember, we were subtracting 3x on both sides. That gives us the subtraction property of equality because we subtracted on both sides of the equal sign. Again, we're going to subtract 20 on both sides so we get all of the numbers, the constants on one side, so negative 26 equals 2x. Again, that was our subtraction property of equality. Next, I'm going to divide both sides by 2. Oh gosh, sometimes when I say things, I write exactly what I'm saying. So negative 13 equals 2. We divide both sides by 2. Wow, sorry, negative 13 equals x. Whew, struggle is real. Okay, that was my division property of equality. And then lastly, if you want to switch sides, you do have to give a reason for why you can do that. And remember, a moment ago we said whenever we have, it's right up here, something that's equal to something new and we switch the sides, that's our symmetric property. So that's my symmetric property of equality because that's that equal sign right there. We're switching on sides of the equal sign. Okay, let's move on to this bottom. We're going to do a geometric proof. And we're going to have you do this from scratch. And so I would be prepared to start thinking through this type of process. But there are definitely patterns to these geometric proofs we're doing. They started by telling us that angle 2 and angle 4 are congruent. So let's write that. That was given to us. That's a good starting point. They want us to prove that this angle is congruent to that angle. So we need to find ways to get those angles into our proofs. Well, if I look like this, you'll notice that angle 2 is red. We've already have that one in our proof. And angle 5 we need. And those two angles are vertical angles because they're created by two straight lines that intersect. So what I'm going to do is make the statement that angle 2 is congruent to angle 5. And I can say that because of the vertical angles theorem. And I like to shorthand it like this just to save a little bit of time. If you want, you can even write VAT, that's fine, but I normally write vertical angles theorem just like that. So let's see. 4 and 5. Sorry, I'm just trying to take a quick break really quick. So we've got 2 is congruent to 5. Looks good so far. So we're going to keep moving on. Why don't we do the same thing over here? Angle 1 and angle 4 are the same. Because they're vertical angles, and that gets angle 1 into the problem. So let's put that in as well. So I'm now going to say that angle 1 is congruent to angle 4. That's the vertical angles theorem again. Okay, well let's take a look here. We want to show that angle 1 and angle 5 are the same. Well, we can't really do that right now because angle 1 is here and angle 5 is here. However, 5 is matched with 2 and 4 is matched with 1. So what I'm going to do really fast is notice that angle 2 is congruent to angle 4 and angle 2 is also congruent to angle 5. So I'm going to make this conclusion here that angle 4 is congruent to angle 5. Is everyone cool with that? So because they were both the same as 2, I can make that statement. Well, now take a look at this. Now I have that angle 4 is the same as angle 1 and angle 4 is the same as angle 5. So using these two, I can now move down here and I can say because of that, that angle 1 is congruent to angle 5. So how did we do those two steps for both 4 and 5? We use the transitive property. This time it's a property of congruence just because we have those congruent signs now. And then for the last step, we also use the transitive property of congruence again. So I know that your mindset, you might still be struggling to figure out how to fill these in. You want to get through as much as you can, but we're also going to practice this more on the review day, so I don't want you to worry too much right now. Here's the other thing. even though there's no Unit 1 practice problems on this review packet, you are still responsible for doing the distance formula, for knowing the midpoint formula, for being able to solve an algebraic problem that means that you have to use linear pairs and vertical angles and setting them equal. So please take a moment and go back and look at that Unit 1 review packet, because you are responsible for that material, and I would not be surprised if you saw at least a couple problems from it, like naming. So here's some things that you might need to know. You might need to be able to name things. You might need to do distance. You might have to do midpoint. And you might also have to do things where like two supplementary angles add up to 180 or a linear pair. You might have to figure out where the things are equal. So go back and take a look at those. And I hope this was helpful.